So hello everyone, thanks for staying for this long, and also apologies for not having a video, and also there might be some background noises all on the presentation, but let's start. Hello everyone, my name is Pei, and this summer I'm working with Dr. Josh Simon on a project searching for globular cluster tidal tails using the Gaia data. Let's start with what globular clusters are. Looking at these images, we can see that globular cluster is extended spherical objects that are gorgeous and within our Milky Way. And if you look at the stars, they're on the redder side, which means that they tend to be older. And because we think globular clusters are the result of a burst of star formation, the assumption is that the stars are of the same age within the cluster. Taking a look at the position of globular clusters within the Milky Way, you can see that they're halo objects, meaning that they don't always fall on the disk. They also tend to have eccentric orbits around around the Milky Way. For example, we have a possible trajectory of Palomar 5 highlighted in red in this picture here. Because globular clusters are extended objects, as they plunge through the disk of the Milky Way and gravitationally interact with the Milky Way itself, it experience differential pulls on different sides of the cluster. That will result in its spherical shape being distorted. This is a simulation from 2005. We can see that the globular cluster starts out spherical, but as it moves through its orbit, it gets stretched into a S-shaped deformation. This is indeed what we observe on sky as well. This is again an image of Palomar 5. Oldenkirk in 2001 used SDSS data and isolated the cluster stars from the field stars, meaning stars that happen to be within the field but does not belong to the cluster. And we're able to identify similar S-shaped tidal deformation on both sides of the cluster. But the challenge, but the thing is that why do we care about the tidal tails, even though they're beautiful? The first thing is that tidal tails can help us trace mass distribution in the galaxy. In 2016, people used the current shape of the Palomar 5 tidal tails to kind of infer two interactions with two small dark matter subhalos. We can see that they simulated two impacts. This is the first one, and there will be another one very soon. Here we go. We can see that from its current shape, we were able to infer what the past of this globular cluster and the stream had been. And it allows us to a way into seeing the past and also tracing dark matters, subhalos that are probably too small to see otherwise. But of course, the challenge is always, how do we select stars that's only within this cluster? If we look at the image of Palomar 5 on sky, it's very difficult to see which one of these stars belong to Palomar 5. This is where Palomar 5 is. But this is, for example, what Oldenkirk got. So this summer, the main problem I'm tackling is how do we select only stars that belong to this cluster? So in order to determine cluster membership, there are some parameters that we can work with. First, very obvious, stars that's within the cluster has to be kind of within a similar patch of sky. So we're selecting stars within 5-degree radius around the cluster center coordinates. That's easy. The second thing we can work with, I mentioned before, is that the stars in the cluster are of similar ages. That means we can take advantage of something that's called an isochrone, corresponding to the cluster age. Isochrone is an empirical line made of positions of stars of different masses on the color magnitude diagram, but of the same age. I'll explain further here. So in this graph, in this plot, on the x-axis is temperature. It also corresponds to color. So this is the bluer end, and this is the redder end. And the vertical axis is luminosity or magnitude in other cases. And the green line is the main sequence. If we look at 30,000 stars evolving, we can see that the more massive stars evolves faster, so it goes on the main sequence first, but then it also moves off the main sequence relatively faster than its lower mass counterparts, and it forms this shape, distinct shape that corresponds to metallicity and the cluster's age. And in my case, the cluster's metallicity is much lower than solar metallicity. So the shape of the isochron corresponding to my clusters usually. The takeaway here is cluster of stars should all fall on this line, and we can definitely use that to our advantage. Let's come back. So for a very long time, this is all that astronomers had to work with. This is a photometric way of selecting stars that belongs to cluster. But with the 2018 Gaia 2 data release, we now have astrometric parameters that we can take advantage of as well. The first thing being the distance to us. So cluster stars, because they're in a cluster, they have similar distance to us, and thus similar parallax. And then the second thing is that the cluster stars are moving in similar direction because they are moving as a clump. So we can use their spatial velocity to do further selection. And just a quick reminder, the radial velocity is the component of the spatial velocity that's along our line of sight, and the proper motion is the component that's perpendicular to a line of sight. Let's translate all of that into image. So now we have, again, something that is very similar to what we just saw. It's also a color magnitude diagram. On the x-axis, this is the bluer end, this is the redder end, and then the magnitude going up on the vertical axis. So this is the raw data of NGC 7099. You can see that there are a lot of stars within this field. It's very hard to determine where the isochron is. But if we apply the astrometric filter, meaning the proper motion and the parallax filter, we can narrow down the cluster the stars that might belong to a cluster a lot more. And you can see that there is a pretty clear isochron. That makes it much easier to evolve a theoretical isochron and fit it to the data. So with the photometric filter, I was able to further select stars that fits roughly on this isochron. Translating all of these onto to on-sky image gives us this. So every star is represented as a black dot. So for all of the stars in the field, you can see this is basically a monolithic black block. With the astrometric filter, we're able to narrow it down so we can see there is an overdensity in the center that corresponds to the cluster itself. The photometric filter narrows it down even more. And for trained eyes, you can probably start to see that there are overdensities over here. But for me, it was very hard at the beginning to identify that. And then even with bin and smooth data, I wasn't able to exactly tell that this is a globular cluster tidal tail. So we went back to drawing board, and talking with Dr. Josh Simon, we decided to, we saw that after, for example, 19th magnitude, anything below that seemed to have a very large dispersion, even with astrometric filter. That means the Gaia data the data quality gets a lot less desirable than the higher magnitude stars. So we decided to also apply a magnitude filter. So discarding all the stars that is dimmer than 19.5 magnitude. With that, we were able to see a pretty clear tidal trace over here. And that is exactly what we see in literature as well. Comparing what I got to Sullivan's paper in this April, we can see that the tidal tail traces match. This is a kind of a mirror image of my image right here, but for example, this overdensity and this overdensity here, the shape matches. So I would call that a success. I applied this algorithm to 7 other clusters and was able to identify some tidal deformation and some tidal tails. In these 3 cases, I was able to observe mostly the tidal tail as it was documented in previous literature. In these three cases, there are some deformation traces that were also identified that was within the literature. So recap of what I've done this summer. First of all, I learned about Python programming and also globular clusters in general. And then I developed the Python-based data reduction pipeline to determine the cluster membership, and which I used to make all these plots that I showed you guys just now. And I was able to recover previously observed tidal tail deformations from literature, these three being the most prominent cases. But things definitely doesn't end here. Next steps. First of all, I will try this algorithm on more clusters, especially ones that haven't had documented tidal deformations or tidal tails. For example, this cluster is one that I wasn't able to find explicit literature on its tidal deformations, but you can kind of see some overdensities around the cluster. It's not clear enough, which brings me to my next step, is to refine the current pipeline so that I can have a smoother image and more smoother image of the tidal deformations. I plan to take into account Gaia's selection bias based on the position in the sky, and also change the absolute cluster membership determination to a probabilistic one. I was doing a straight cut in, for example, the astrometric and the holometric filters. But hopefully these two efforts will make the plot in the end a lot more smoother. And then on the software side, I plan to make this pipeline into Python package so that astronomers can use it more readily to identify tidal tails or tidal deformations clusters that they want to study. Hopefully that will help give some insight into, for example, the history of the cluster, and possibly also help with the dark matter researches. So this is the end of my talk. I want to take the time to thank Dr. Josh Simon for being my advisor this summer, to Gwen for hosting this CASSI program, and Dr. Tim Lee and also Alex for all the technical support along the way. And everyone else at Carnegie that helped me through rough patches as well. Thank you very much, and welcome questions.
All right, nice job, Pei. Questions for Pei about tidal tails?
I have a question, Pei, about, I think it's 1799, NGC 1799.
Yes.
This weird sharp angle in the tail. Normal tidal tails are pretty symmetric. So if I see it on one side and want to believe in it, I would have thought one should see it on the other side, but I at least don't. And the second, has anyone come up with an explanation why there should be such a sharp turn in a tidal tail?
That's a great question. And I wasn't able to really figure that out either. So let's take a look here. So for example, in Solomon's paper, which was the paper I was comparing my result to, it also had kind of a sharp turn right here. We can see that like there are corresponding tidal tails on the other side, but there didn't seem to be like a very sharp turn, at least not exactly what I observed. It could be due to, for example, like disturbances similar to what Palomar 5 had gone through, but I wouldn't have any way of knowing at this point, but that's a good question. I think those are for next step researches.
Okay, thank you.
Thank you.
Any other questions for Pei?
I have a comment, not a question. So I think it will be good for you to also overplot the proper motion of the galaxy along with the tails and see if they align, because if it's really the tidal tail and the proper motion after correcting the solar motion should align with the orientation of the stream or the tail.
Okay, yes, that's a great point. In Solomon's paper, you can kind of see that this is the orbit and this is the direction to cluster, the galactic center. It didn't plot the proper motion. I actually made some plots with proper motion on it But I think I made some mistakes, and I was talking to Josh about this yesterday, I think. So it's in the next step, but it wasn't ready, so I didn't show it in my presentation. But that's a great suggestion. Thank you.
All right. Any other questions or comments for Pei?
Nobody else has one. I'll come with a second one. Can you say a little bit more about, you mentioned biases in the Gaia, I think, in the Gaia proper motions, or what are biases that are known
in the Gaia selection based on the position in the sky? So what I mean by that is that because Gaia was scanning the sky, it's a little patchy. So of the 1 second, a plot of one of the most prominent ones. Let's see. So it's NGC 5133. Sorry, 39, I think. It will have a pretty clear. It will show pretty clearly what I meant. Here we go. How do I share screen again? Here. Sorry that this is kind of messy, but you can see that, for example, right here, no, not this one. But for example, here, you can see that this is like on sky plot of after some selection, not all of the selections I've done, but you can see that there are fringes in the stars that are represented by the Gaia data set. It is due to basically the position, because Gaia was scanning data like this. So it misses some spot, and some spot have less precision. So when I was doing some precision cuts, it got cut off.
Okay, thank you. How weird.
Yeah.
Wow.
Any other questions for Pei?
I have
All right,
one.
very nice. Oh, go ahead.
Pei, so you can identify some of these by eye a little bit, and you've showed that they match the literature, but is there a metric that you use going forward for what makes a tidal tail and what doesn't? How will you sort of quantify that?
Right, I think that's in the next step. Whoops, I forgot to write that. But the next step, I would probably try to do some contour plots, so that and refine what the statistical metric is. But right now I'm kind of going by eye and trying to just see that I was able to use this algorithm and find some deformations.
Perfect. All right. Thank you so much, Pei. Very nice job.
Thank you.